Alright, welcome to this third video for Unit 3. This is actually the last video for Unit 3, which is quite surprising if you ask me. But, yeah, like I said in the last video, we're going to be talking about Atwood Machines. Let's get right into it. Atwood Machines, in general, it features a string that has a mass on both ends, which go up, down, whatever. It depends on the setup of the Atwood Machine. The string, it's usually looped around a pulley. That's kind of the basics of an Atwood machine. There are three main types of an Atwood machine. All three types assume that this pulley has no mass, the string has no mass, and there's no friction of any kind. That means no air resistance. Air resistance is a type of friction. I forgot to mention that in the last video, I think. And no friction between the string and the pulley, because that would interfere with our calculations. But yeah, let's get into it. Let's see. We're going to start with the normal Atwood. A normal Atwood, in general, it looks like this. We have the pulley, string, forgive my bad drawing. We have one mass down here. We'll call that one M1, and we'll call this mass M2. Um, Now, obviously, we don't necessarily know which way it's going, but we're going to assume that it's going this direction. And the thing with Atwood machines is that when it goes in this one consistent direction, that is usually the positive direction. So in this case, the positive direction for M1 is up, but for M2, it's going down. That's an interesting thing with Atwood machines that isn't really common with any other thing. But keep that in mind, because that's a part of this whole mess, I guess. I think mess is the best word. Uh, Throughout these three Atwood machines, I'm going to just go through how we can find the acceleration of the blocks. Because these two masses in an Atwood machine, they always accelerate at the same rate. No matter what type of Atwood machine it is, they're going to still accelerate at the same rate. So we're going to try to find that acceleration for all three of these Atwood machines. Okay. Uh, this first one, the best way to start, really, I think, is to draw some good old free body diagrams. So this can be M1. And there are two forces acting on M1. There's the force of gravity, which is mg, but I'm going to say it's m1g because there's two different m's. And it's also the force of tension, right? And we know our positive direction is up in this case. So the sum of the forces on 1 must equal the mass of 1 times its acceleration, which in this case is t minus m1g. That equals m1a. I'll come back to that in a second. Now we're going to take a look at m2. M2 has a very similar free body diagram. It has a force of gravity pointing down, but it's m2g this time. And it has a force of tension pointing up. However, for this one, the positive direction happens to be down. So this means that the sum of the forces on 2 is equal to its mass times its acceleration, which is the same. That's why there's no subscript. This means that m2g minus tension is equal to m2a. Now I'm going to rearrange these equations to isolate for t. This first equation is fairly easy to isolate. T is equal to m1g plus m1a. That's it. The second one, though, it's slightly more complicated, but if you work through it, it's just m2g minus m2a equal to tension. Now, because both of these are equal to tension, the tension in the string, of course, is the same for both objects. Now I can put these together and set them equal to each other because they're both equal to tension, which is the same thing. So m1g plus m1a, I'm going to abandon color coding now because it's way too much work, equals m2g minus m2a. Now I'm going to do some rearranging of this equation. I'm going to bring the m2a term to the other side. That makes it so it's m1a plus m2a. And I'm going to bring the m1g term to the other side as well. So that gives m2g minus m1g. On this left side, I'm going to factor out a. So that's a times the quantity m1 plus m2. The other side, I'm going to factor out g to get m2 minus m1. And then I divide both sides by m1 plus m2. And this just gives that acceleration is equal to g m2 m1 over m1 plus m2. And that's the acceleration of of the blocks in this Atwood machine. Uh, do note that you shouldn't try to spend time and memorize all of these. It's not a good idea. It's not really a good idea to try to memorize these. What you do want to know though is you want to know how to derive these equations. You want to know how to get to this final destination of that mess. Don't try to memorize it. It's a little too much work, frankly. Uh, just know how to get to this equation. There is an alternative way of finding the acceleration where it just looks at the system as a whole, and it's actually quite interesting. Uh, Hold on, give me a sec. Yeah, so if we look at the system as a whole, then the sum of the forces acting on the system must equal the mass of the system times the acceleration, not equals acceleration. My bad. Now the total, the sum of the forces acting on the system, it's going to just be the force of gravity on block 2 minus force of gravity on block 1, because the force of gravity on block 1 is acting in the negative direction. And there's no tension whatsoever because the tensions in the string cancel out. So then we get m2g minus m1g. The mass of the system is m1 plus m2. This is equal to acceleration, and this looks, whoops, not equal to. I made that mistake again. This looks eerily similar to these steps around here. Yeah, it's just a quicker way to get to it. However, it's not so intuitive for every person. So if you know both methods, then that's obviously great. If you know one method, that's fine too. Just do whatever makes sense for you. That's it for a normal Atwood. Let's move on to the next type of Atwood. The next type of Atwood is called a modified Atwood. In a modified Atwood, instead of both of them being dangling down one end, one of the blocks, it's kind of it looks a little more like this. Okay, this is getting small. Let me zoom in here. I'm zooming in on mine, not necessarily yours, so don't get too mad at me. Oh. M2 is here, but one of the masses in this case is going to be M1. It just sits on this table. That's what it does. Now, of course, we're assuming there's no friction on this table, so, the only force acting... Actually, no. You know what? Yeah, let's just get into it. We're going to start drawing free body diagram. Actually, no. We need to first establish a positive direction. The positive direction is going to be this way. It's going to be the direction that M2 falls. That's the positive direction. Now we can get into drawing free body diagrams. So we have M1. We have the force of gravity as always. I'm just going to write it as F of G at this point because it doesn't really matter. The normal force opposes this. The two are of equal magnitude because of Newton's... Actually, no, not even a particular law. It's just that, actually, no. I think the best law would be Newton's second because there's no vertical acceleration. That means the sum of the forces in the vertical direction has to equal 0. However, there is another force acting on M1, and that is force of tension. So that's that. We can write our Newton's second law equations. F sub 1 is equal to M1A. In this case, there is only one force that's causing M1 to accelerate. That's the force of tension. That's equal to M1 times A. That got really sloppy handwriting. Who cares? I'm going to go with that. Time for M2. M2, it's a fairly simple diagram again. It's going to be F of G. No, this one I'm going to write as M2G. And this time, instead of force of normal, it's going to be force of tension. We can write out the Newton's second law equations. Let's see, that's going that way. So let's see, that to A. So then M2G minus tension is equal to M2A. Now with this, because the pink equation, it's already isolated for T, I think I'm just going to plug it into the second equation. So then we get M2G minus M1A is equal to M2A. I'm going to bring M1A to the other side. M2G is equal to M1A plus M2A. This, if I factor out the A term, then I get that. And then if I divide both sides by M1 plus M2, then I just get acceleration is equal to M2G over M1 plus M2. That's that. This one, the equation is a lot more simpler than the normal Atwood. Again, just like the normal Atwood, we can look at this from a perspective of the whole system. So the sum of the forces acting on the system is equal to the mass of the system times the acceleration. Not going to write an equal sign again. In this case, the only force that acts on the system as a whole is going to be the force of gravity that acts on M2, because other tensions again they cancel out, right? So yet again, we get M2G is equal to M1 plus M2. That's the sum of the system, the sum of the mass of the system, I should say, times its acceleration. And yet again, this looks quite similar to the steps down here. So we arrive at the same answer. Again, doesn't matter which way you approach it, as long as if you get the correct answer in the end, right? One more type to go. This type, it's called a half Atwood. Half Atwood. I can't spell Atwood, apparently. Okay. Do note that it also might go by other names. Sometimes people call it a tilted Atwood. It might be also called an inclined Atwood. The reason why this is the case is because it's an Atwood machine, or a modified Atwood machine, except instead of a level surface, it's on an incline. I'm going to make this angle theta. That's a right angle. Trust. That's the little pulley. That's my string. That's a string. So that's M2. And that is M1. Now, with half Atwood, we, again, don't really know which direction it's going to go. But we're going to assume that M2 is falling. M1, of course, could be going down the incline, depending on the situation. But we're just going to say that that's the positive direction. Now we're going to draw out our free body diagrams as usual. This is normal procedure at this point. We have M1 tilted. That is going to be the normal force going that way. Again, it's perpendicular to the surface. Force of gravity. And we have the force of tension. Right. Now, here we want to split up the force of gravity into components. So this is going to be a component diagram now. It's going to be quite similar. We're going to still have this. Probably should label that as M1. But now we have a force of gravity component. I'm going to write this as M1G now. And this vertical-ish component, it's going to be cosine of theta. The reason why this is the case, I'm going to draw a triangle. This is going to be a very big triangle. Okay. This is my angle theta down here, right? That's a right angle. Just pretend it is. My force of gravity vector, it kind of does this, right? We know it's perpendicular. Oh, wait, no. Whoops. No. Force of gravity is actually straight down, right? Now, what we want to do is we want to split this into two components. We want to split it into this component and the horizontal component, right? Kind of like that. Now, because those two are a vertical and a horizontal, that's a right angle there. Because force of gravity comes straight down, this is another right angle. This means that this angle up here, it's 90 minus theta. Now, we know that that angle, it's a right angle too. This is a really bad diagram. So that means if this part is 90 minus theta, then this part is theta. And now we can see that, so this part's force of gravity, right? Now that we have this, that's too small. That's a little better. Theta f of g. Now we can see that this is fg cosine theta, and this is fg sine of theta. That's why it's cosine theta. Do note that it's not necessarily always cosine is vertical, sine is horizontal. It's going to depend on each basis, so you're going to want to make sure that you're using the correct trig function. And similarly, I mean, kind of outlined it briefly, but there's going to be a force of gravity component that goes that way, and it's going to be times the sine of theta. Again, we can start writing out our equations. With this, the positive direction is that way. So that means, let's see. That means tension minus m1g sine theta equals m1a. And then for m2, its free body diagram is so much simpler. Yet again, we have force of gravity and tension. Who would have guessed? Also, I probably should say that none of these vector lengths are perfect. Because the force of tension in the string, it's supposed to be equal. Like, this these two vectors, they really should be the same length. I'm just being lazy and I'm not doing it. But in an actual, like, for example, like in the AP test setting, you want to draw it quite accurately, and that will include drawing those lengths relatively accurately. In fact, it's even so extreme where like you want to draw it such that this gravity component and like you want to eyeball it so that the vertical component and the normal force are going to be about the same because there shouldn't be any acceleration along that axis, right? Anyway, then got on a little bit of a tangent there. Let's write out our equation for M2. Positive direction, it's straight down. I'm not making that green this time, sorry. So then force of gravity, which is M2G, minus tension is equal to M2A. This one I'm going to isolate for T. M2G minus M2A is equal to tension. Now that both of these, no wait, I still have to isolate this first one for T, which is actually pretty simple. Plus M1G sine theta. Now that both of these are equal to tension, I can set them equal to each other. So let's see, M1A plus M1G sine of theta is equal to M2G minus M2A. Similarly to the normal Atwood, I'm going to rearrange it so that all my A terms are on one side, all my G terms are on the other. Now I have M1A plus M2A is equal to M2G minus M1G times the sine of theta. Now I can factor things out. M2, factor out the G. And then I divide to just get this. M1 plus M2. And again, just like all of the other Atwood machines, I can look at this from a perspective of the whole system. So sum of the forces on the system is equal to the mass of the system times the acceleration. I didn't write an equal sign this time. Kind of just like all the other ones, the tensions cancel out so that now the only forces are this component of gravity over here and this gravity. Positive direction means the force of gravity on M2 comes first. M1G sine theta. This is going to be equal to M1 plus M2 times A. And yet again, this is very similar to one of the equations that we got down here. It's like, yeah, no, it's just this one, but without the G factored out. Again, though, just go with whatever approach you find best. If you want to look at it from a system perspective, you do you. If you don't want to look at it from the perspective of the system, again, you do you. I'm not going to stop you. Why would I? And yeah, like I said, sort of near the beginning of this video, don't memorize these. It's not really worth it. What you want to do though, just know how to approach it. The best way to approach it is with free body diagrams and using Newton's second law. Newton's second law is like one of your best friends in this course. In fact, like I'm pretty sure in some FRQs, like if you just write F equals ma, you can get a point. Like that's how important using Newton's second law is. You just write down F equals ma and boom, you get a point. Newton's second law is just that important, I guess. It's so special. Yeah, I think that's gonna wrap it up for this video, and with that, the unit for Unit 2, Dynamics, that's gonna come to a close as well. Just like with Unit 1, there will be a practice problem document. I will link that in the description. I think it's 7 practice problems this time around. I'm not exactly sure, but it's in that area. Yeah, again, answers and explanations will be available. Yeah, I'll see you next in Unit 3, where I can't talk. We will be talking about energy. I'll see you there.